Betelgeuse, also designated Alpha Orionis, is the ninth brightest star in the night sky and second brightest in the constellation of Orion. Distinctly reddish, it is a semi-regular variable star whose apparent magnitude varies between 0.0 and 1.3, the widest range of any first-magnitude star. Betelgeuse is one of three stars that make up the Winter Triangle asterism, and it marks the center of the Winter Hexagon. It would be the brightest star in the sky if the human eye could view all wavelengths of radiation. The star is classified as a red supergiant of spectral type M1-2 and is one of the largest and most luminous stars visible to the naked eye. If Betelgeuse were at the center of the solar system, its surface would extend past the asteroid belt, wholly engulfing Mercury, Venus, Earth and Mars. Calculations of its mass range from slightly under 10 to a little over 20 times that of the Sun. It is calculated to be 640 light-years away, yielding an absolute magnitude of about -6. Less than 10 million years old, Betelgeuse has evolved rapidly because of its high mass, having been ejected from its birthplace in the Orion-OB1 association, which includes the stars in Orion's belt. This crimson runaway has been observed moving through the interstellar medium at a supersonic speed of 30 km per second, creating a bow shock over 4 light-years wide. Currently in a late stage of stellar evolution, the supergiant is expected to explode as a supernova within the next million years. In 1920, Betelgeuse became the second star to have the angular size of its photosphere measured. Recent studies have reported an angular diameter ranging from 0.042 to 0.056 arcseconds, with the differences ascribed to the non-sphericity, limb darkening, pulsations, and varying appearance at different wavelengths. It is also surrounded by a complex, asymmetric envelope roughly 250 times the size of the star, caused by mass loss from the star itself. The angular diameter of Betelgeuse is only exceeded by R Doradus. Nomenclature: Alpha Orionis is the star's Bayer designation. The traditional name Betelgeuse is derived from the Arabic Ibti al-Jawza, meaning the axilla of Orion, or Yad al-Jawza, meaning the hand of Orion. In 2016, the International Astronomical Union organized a working group on star names to catalogue and standardize proper names for stars. The WGSN's first bulletin of July 2016 included a table of the first 2 batches of names approved by the WGSN, which included Betelgeuse for this star. It is now so entered in the IU catalogue of star names. Observational history: Betelgeuse and its red coloration have been noted since antiquity. The classical astronomer Ptolemy described its color as pi omicron kappa iota rho rho omicron sigma, a term that was later described by a translator of Alu-Beg's Zij Sultani as rubedo, Latin for ruddiness. In the 19th century, before modern systems of stellar classification, Angelo Secchi included Betelgeuse as one of the prototypes for his Class 3 stars. By contrast, 3 centuries before Ptolemy, Chinese astronomers observed Betelgeuse as having a yellow coloration, suggesting that the star may have spent time as a yellow supergiant around the beginning of the Common Era, a possibility given current research into the complex circumstellar environment of these stars. Nascent discoveries: the variation in Betelgeuse's brightness was first described in 1836 by Sir John Herschel, when he published his observations in Outlines of Astronomy. From 1836 to 1840, he noticed significant changes in magnitude when Betelgeuse outshone Rigel in October 1837 and again in November 1839. A 10-year quiescent period followed. Then in 1849, Herschel noted another short cycle of variability, which peaked in 1852. Later observers recorded unusually higher maxima with an interval of years, but only small variations from 1957 to 1967. The records of the American Association of Variable Star Observers show a maximum brightness of 0.2 in 1933 and 1942, and a minimum of 1.2 observed in 1927 and 1941. This variability in brightness may explain why Johann Bayer, with the publication of his Uranometria in 1603, designated the star Alpha, as it may have rivaled a usually brighter Rigel. From Arctic latitudes, Betelgeuse's red color and higher location in the sky than Rigel meant the Inuit regarded it as brighter, and one local name was Aluriajuak, large star. In 1920, Albert Michelson and Francis Pease mounted a 6-meter interferometer on the front of the 2.5-meter telescope at Mount Wilson Observatory. Helped by John Anderson, the trio measured the angular diameter of Betelgeuse at 0.047, a figure which resulted in a diameter of 3.84 times 108 kilometers based on the parallax value of 0.018. However, limb darkening and measurement errors resulted in uncertainty about the accuracy of these measurements. The 1950s and 1960s saw two developments that would impact stellar convection theory in red supergiants: the stratoscope projects and the 1958 publication of Structure and Evolution of the Stars, principally the work of Martin Schwarzschild and his colleague at Princeton University, Richard Harm. This book disseminated ideas on how to apply computer technologies to create stellar models, while the stratoscope projects, by taking balloon-borne telescopes above the Earth's turbulence, produced some of the finest images of solar granules and sunspots ever seen, thus confirming the existence of convection in the solar atmosphere. Imaging breakthroughs. Astronomers in the 1970s saw some major advances in astronomical imaging technology, beginning with Antoine Labeyre's invention of speckled interferometry, a process that significantly reduced the blurring effect caused by astronomical seeing. It increased the optical resolution of ground-based telescopes, allowing for more precise measurements of Betelgeuse's photosphere. With improvements in infrared telescopy atop Mount Wilson, Mount Loch and Mauna Kea in Hawaii, astrophysicists began peering into the complex circumstellar shells surrounding the supergiant, causing them to suspect the presence of huge gas bubbles resulting from convection. But it was not until the late 1980s and early 1990s when Betelgeuse became a regular target for aperture masking interferometry that breakthroughs occurred in visible light and infrared imaging. Pioneered by John E. Baldwin and colleagues of the Cavendish Astrophysics Group, the new technique employed a small mask with several holes in the telescope pupil plane, converting the aperture into an ad hoc interferometric array. The technique contributed some of the most accurate measurements of Betelgeuse while revealing bright spots on the star's photosphere. These were the first optical and infrared images of a stellar disk other than the Sun, taken first from ground-based interferometers and later from higher-resolution observations of the COSE telescope. The bright patches, or hotspots, observed with these instruments appeared to corroborate a theory put forth by Schwarzschild decades earlier of massive convection cells dominating the stellar surface. In 1995, the Hubble Space Telescope's faint object camera captured an ultraviolet image with a resolution superior to that obtained by ground-based interferometers, the first conventional telescope image of the disk of another star. Because ultraviolet light is absorbed by the Earth's atmosphere, observations at these wavelengths are best performed by space telescopes. Like earlier pictures, this image contained a bright patch indicating a region in the southwestern quadrant 7 quintillion 3 quadrillion 200 trillion spadesu 2000 K hotter than the stellar surface. Subsequent ultraviolet spectra taken with the Goddard high-resolution spectrograph suggested that the hot spot was one of Betelgeuse's poles of rotation. This would give the rotational axis an inclination of about 20 degrees to the direction of Earth, and a position angle from celestial north of about 55 degrees. Recent studies. In a study published in December 2000, the star's diameter was measured with the infrared spatial interferometer at mid-infrared wavelengths, producing a limb-darkened estimate of 55.2 plus or minus 0.5 milliseconds, a figure entirely consistent with Michelson's findings 80 years earlier. At the time of its publication, the estimated parallax from the Hippocos mission was 7.63 plus or minus 1.64 Mars, yielding an estimated radius for Betelgeuse of 3.6 astronomical units. However, numerous interferometric studies in the near-infrared made at the Paranal Observatory in Chile argue for much tighter diameters. On the 9th of June 2009, it was announced that the star had shrunk by 15% since 1993 at an increasing rate without a significant diminution in magnitude. Subsequent observations suggest that the apparent contraction may be due to shell activity in the star's extended atmosphere. In addition to the star's diameter, questions have arisen about the complex dynamics of Betelgeuse's extended atmosphere. The mass that makes up galaxies is recycled as stars are formed and destroyed, and red supergiants are major contributors. Yet the process by which mass is lost remains a mystery. With advances in interferometric methodologies, astronomers may be close to resolving this conundrum. In July 2009, images released by the European Southern Observatory, taken by the ground-based Very Large Telescope Interferometer, showed a vast plume of gas extending 30 astronomical units from the star into the surrounding atmosphere. This mass ejection was equal to the distance between the Sun and Neptune, and is one of multiple events occurring in Betelgeuse's surrounding atmosphere. Astronomers have identified at least 6 shells surrounding Betelgeuse. Solving the mystery of mass loss in the late stages of a star's evolution may reveal those factors that precipitate the explosive deaths of these stellar giants.